So I'm presenting Michael's work. It's Michael's project, and I hope I'm in a good position to deliver it to you in the right way here. So in my group, we are, among others, interested in dynamic analysis of concurrency issues. Yeah, and now that in the near future, or actually right now, you can finally run concurrent programs also in WebAssembly, we thought it might be interesting to have tools to investigate these problems also on the Wasm platform. So therefore, the approach that we are familiar with is offline dynamic analysis, which means we are kind of instrumenting the runtime environment with tracing, and then we collect execution traces, and then offline we are analyzing the execution traces to do prediction of data races, prediction of deadlocks. And one part is I would like to get your feedback if this is a tool that's interesting for you guys, if it's needed, what further developments are interesting here. Right. So I guess I can go pretty quickly over the first few things. Essentially, one difficulty that I'm saying we, but it should really be Michael all the time, that we encountered while setting this up was that Wasm runs essentially in a well-specified embedder, but the embedder could be like anything. It could be a standalone Wasm runtime, it could be a browser, and any services that are provided are really provided via these external objects. Now, like if the embedder has a chance, offers concurrency as a service, then it's via these external objects. Right. So then you got WebAssembly modules, and you all know the components of that. So you essentially have tables with references to functions and to external objects. Then when you instantiate a WebAssembly module, it obtains linear memory from the embedder. Globals are initialized, and finally you have the instructions that do their job. And well, I guess I don't really have to explain anything of that to you. So let me go over that fairly quickly. So the main thing that we learned when investigating it is essentially that you could have a single module, and then when it comes to concurrency, you can have several instances of this module running in the embedder. So that means here you have one instance, you could have a different module that is also instantiated, and then essentially they work separately. So here you have a separate memory instance, and everything is completely disjoint between the two. And one part of our journey was to discover how you can actually create a shared space where two things can actually communicate in shared memory, like when you're translating a Rust program or even a C++ program into Wasm. Right, so what we need for multi-threading, which is provided by some of the embedders, is we need some sort of atomic memory operation instructions, we need wait notify, mutex implementations, and we need to somehow obtain this shared linear memory, which isn't usually provided. Right, so this is the situation that we had before. So now this is what we would like somehow to obtain. And unfortunately, you have to jump to a couple of hoops in order to achieve that. Right. So what we did in order to achieve that, actually that was like the second iteration, we thought, okay, so first we're going to insert an abstraction boundary so that we can abstract over the differences of the embedders. Yeah, so the first step here kind of provides a what did he call it? Oh, he has a name for it. An ABI through which our object programs, well, the WebAssembly modules can uniformly access the concurrency services from the underlying embedder. And this is kind of specific for every embedder, but on top of that, later on we want to talk about tracing, and that's going to be oblivious of the particular embedder that is below. Now, therefore, trace generation runs on top of that, because otherwise, I mean, before the first version, we had essentially two different modules for this trace generation, one for a standalone runtime and one for the embedded JavaScript runtime. And that felt like a bit wasteful, and also we felt that this lower level would be an interesting contribution, interesting module by itself. Right, yeah, so that's what it's looked like. So this is kind of the bottom layer of the previous diagram. This is the internal runtime ABI, and then on top, and then this would run on top the native embedder or the JavaScript embedder, and you have to set them up in quite different ways. And the execution tracing would live somewhere inside here. So what does this ABI look like? It essentially consists of some imports and exports. Essentially, the imports are kind of what your module you want to run, the threading primitives that it can use, and then the other ones here you have to notify our framework about thread starting and obtaining memory and freeing memory. So that's what this ABI roughly looks like. When it comes to tracing, then we actually need some more, but we'll come to that in a few minutes. So I think 5 minutes or how much?
You have over 10 minutes left.
Over 10 minutes. Okay, that should be plenty. So now we can get to this issue of getting to shared memory. Right. So if I have a module, then you instantiate it, and usually you get this memory instance. You can do another instance, and this is usually not the way that it's set up. Yeah? So we would like it to, if we want to have these two threads communicate, we would really like them to refer to a single memory instance. But if you straightforwardly instantiate it, it's not happening this way. So, but nevertheless, for each thread, you have to create a new instance of the WebAssembly module in order to get started. So, so depending on which way we want to run it, so with our infrastructure, you can either run it straightforwardly. You first have a patch phase, which I will get to in the next slide, which kind of explains how you squeeze the different instances into the same memory, and then execution. And in the other case, you also, when we want to trace, we also have this patch phase. This is then followed by instrumentation, execution, and during execution you generate traces, and then you get a trace essentially in a standard format that's used by various tools, written by us and also written by other people in the field. Right. Now, so if we were naively creating different instances that all point to the same linear memory, then we're in trouble, because the standard instantiation maps static data somewhere. Maybe that's okay, but then it also has allocates a stack area, and if we are naive, then all the stack pointers of our 3 instantiations of the module, they all point to the same area. Okay, this is not a good idea. So there are tools around, namely Wasmgrind, which does some patching, and it essentially creates a layout like this. Yeah. So sorry. So only the first instance gets the normal space for the stack. The static data is shared among everybody, and then for the remaining instances, the stack is actually allocated in the heap. Then there's thread local storage, which is also allocated in the heap. What is currently unclear to us is how you make sure that this allocated stack space is actually enough. I mean, you would probably have to have some analysis if you can do that. We didn't do that, and we didn't find that specified somewhere. Now, so basically for for our ABI, we mimic pretty much what Wasmgrind was doing and extended it so that it worked with our stuff as well. All right, so we're getting pretty much to the end. So if you actually want to do this tracing, our tracing tool, we looked around on the market, and the only one that was working at that time was ABI. So for tracing, we extend the ABI that we don't just get, that we don't just get the usual threading messages, but that we also get messages when there are read and write operations to the shared memory. Right. That's actually pretty much it. From that, you can generate records that contain all the information that is required for this rapid bin format, which is then the input to our tools. And unfortunately, since I'm not Michael, I'm not really able to show you a demo of that, so he would probably have done that. So that's all I have to say. Thank you very much.
So you've single-handedly put us back on schedule, so we don't do the rush thing. If anyone would like to ask some questions with the slides, please come up to the microphone. Can we get that microphone activated?
Hi, I'm Burak from working for Google these days. And did you find any bugs?
Not yet, not yet. So we right now, we just got the stuff more or less to work, and there are a couple of smallish examples that we were running. And now in the next phase, so Michael is working on his master's thesis. So the idea for the master's thesis is to actually find a nice corpus of concurrent Rust programs and see what the tool does with those. And so if any of you has suggestions for what programs would be useful, because this is actually a real pain factor, because you need to find programs that use concurrency somehow in a meaningful way, that are not too big. Then you need to configure the inputs. So it's a lot of work to build such a benchmark suite. Yeah, and it seems that Michael is actually interested in doing that. And so any input there would be really very welcome.
Excellent, thanks.
So for that, I suggest talking to Arjun. He's done a little bit of work on race detection for WebAssembly.
Right.
So about this binary format, this rapid bin, what kind of tools do you have that consume this, and do they work like in a streaming fashion? Are they offline tools?
So they're essentially offline tools. So the rapid bin format is a compressed binary format for these traces, and that's conceived by there's a famous group. Here, these guys here. Umang Mathur, maybe he's even here. So he's in Singapore. So he has built huge tool sets that work on this format, and many other tools, well, from researchers in that area also work on that.
Cool.
So that's why we chose it.
Cool.
So Chris Woods from Siemens, and I can't give you Rust examples just yet, but I can give you a huge body of C-based concurrent examples, and we're bringing them to WebAssembly, and your stack observation and knowing when you're bringing code over what the stack size should be is a big problem, and we go into it, and I am happy to give you a whole bucket load of examples. Please come see me afterwards.
Yes, excellent, thank you. Great.
I'm sorry to ask a technical question, but for the off-the-web side of threads, are you using the WASI threads interface or something else?
I should defer that to Michael. I'm sorry. So he did all the technical stuff.
No, that's perfect. Thanks so much. Let's thank the speaker one more time.
Thank you.
Oh, sorry. We actually, no, let's change it. you have one more question. We do actually have time. Please ask it, and John, please come up.
Thank you for the talk. I have a question about the algorithm that you use. About the algorithm for checking the data race deduction.
Yeah.
Were there any challenges, or could you just use it out of the box, or did you have any changes to the algorithm that you needed to?
So okay, yeah. So since we are using the standard format, we can use tools that are available. We also developed some of our own tools, but I mean, so Mature and friends have lots of tools that are well tested and well published. So
okay, thank you.
all right.